Good afternoon, and second sitting of how things were seen in 1961. Two opposing. So now we're trying to push that away. So I put two side by side just to see what they do. Will it make it over to the other side? Right, so 1961. So I finished off with, therefore, any theory about the birth of the Earth takes a common origin of the planets for granted. After examining the facts about the planets and keeping in mind the orderly arrangement and working of the solar system as a whole, the astronomer is ready to work out his own theory as to the origin of the solar system and of the Earth itself. So, like I said, you'll start to hear, it's like a story. All the names that come up. In 1755, Immanuel Kant, the German philosopher, suggested that the solar system, the sun, the planets, the moons, of which there are 30, the asteroids, the comets, and the meteors, was formed from a nebula. There are many nebulae, great masses of thin and veil-like gas scattered throughout the universe. You may be familiar with the Great Nebula in the constellation Orion, which is just visible to the naked eye on a clear winter's night. Kant's theory, however, did not cause much of a stir in the scientific world. The great French naturalist Georges Louis Leclerc, Comte de Buffon, wrote in this same general period his own answer to the question as to how the Earth was born. Buffon was the author of a very famous work on natural history in 44 volumes. It was in this great work that Buffon gave his theory of the origin of the Earth and the other planets. He believed that ages ago the sun collided with another heavenly body which he called a comet. Now listen to this. Actually, what he probably meant was not a comet but another star. Rather little was known at that time about the nature of comets. He suggested that such a collision would force a great deal of material out of the sun and that this material would cool and become the planets. When we later examine theories that were widely accepted during the first half of the 20th century, we shall see how very modern Buffon's ideas concerning the formation of the planets proved to be. It's so easy to insert stuff like this. It's just, I suppose it's one of those where you can either see it or you can't. Pierre-Simon Marquis de Laplace, a French mathematical astronomer, rejected Buffon's theory and offered his own. This was the first one to be widely accepted. Laplace's ideas about the birth of the Earth and the solar system are set forth in his nebula hypothesis, a clever theory that won wide attention. A hypothesis is a scientific theory that is based on observed facts, or at least does not contradict them. The nebula hypothesis imagines first the tremendous explosion of a star that, according to Laplace, later became the centre of the solar system. Exploding stars, which are not at all common, are known as novae, or new stars. This name was given them originally because when a faint star exploded and became suddenly very much more brilliant than it had been before, it was often mistaken for a new star in the heavens. As a result of Laplace's explosion, the hypothesis suggests the sun expanded until the vast fire mist of which it was made extended out in a gigantic nebula beyond the orbit of the outermost planet to be. In other words, all of the future members of the solar family were then part of an enormous whirling mist of incandescent gases. In the beginning, they had no form and no individuality, but were blended in the parent nebulous mass. Laplace, of course, lived long before the discovery of the ninth planet Pluto. Even Neptune had been discovered just the year before he died. The diameter of the nebula must have been, if Laplace was correct, over 4,000 times the present diameter, 864,000 miles of our Sun. Laplace thought that the planets were formed from rings of gas. Right, we can skip all this one. Right, I'm just going to pause you. Okay, and we moved on. So another bit called What is Life? Remember, I'm just going page after page. And what we have here is an investigation of tobacco mosaic leads to the discovery of viruses. Viruses were discovered by the Russian scientists Iwanowski in 1892 while he was investigating the plant disease called tobacco mosaic. The general belief at the time was that the disease was caused by bacteria, tiny plants which can be seen only under the microscope. It was known that bacteria can be removed from the liquids in which they live by means of a very fine filter made of porcelain or compressed earth. The liquid will pass through the filter, but the bacteria will not. Iwanowski showed that he could produce tobacco mosaic in healthy tobacco plants by inoculating them with the juice of diseased plants, even after the juice had been filtered, in order to remove bacteria. He came to the conclusion that certain diseases are caused by agents that can pass through the finest filters. Other scientists confirmed Iwanowski's findings. The newly discovered disease agents were called viruses. Virus is a Latin word meaning poison. They are sometimes called filterable viruses because they can filter through any porous mass. They are also known as ultramicroscopic viruses because they cannot be seen through the ordinary microscope. In the course of time, it was learned that viruses produce many diseases in both animals and plants. They cause more than 70 diseases in man. Among these are smallpox, yellow fever, measles, chickenpox, colds, influenza, infantile paralysis, mumps, rabies, and encephalitis, sleeping sickness. It is possible nowadays to filter viruses through a special type of membrane. We still cannot see them through the ordinary optical microscope, but the electron microscope enables us to make shadowgraphs of viruses, and these shadowgraphs show tiny particles that have a definite size and shape. The particles, it is true, may not be viruses. They may be crystalline forms that contain the viruses. The viruses for a particular disease, the crystals containing these viruses are all of the same size and shape. Viruses resemble living things in certain respects. They can adapt themselves to their environment. They can multiply. In certain cases, at least they contain the chemical compounds known as proteins. And as far as we know, proteins are found only in living protoplasm. On the other hand, the researches of Dr. Wendell M. Stanley tend rather to show that viruses are non-living things. Stanley won part of the Nobel Prize for Chemistry in 1946 for his work on viruses. In 1935, he separated fine needle-shaped rods, crystalline in form, from plants infected with tobacco mosaic. Even after dissolving and precipitating the rods repeatedly, he was still able to produce disease with them. Stanley argued that if the rods were living organisms, they probably could not live after being subjected to this treatment. It is clear, therefore, that we cannot classify the viruses definitely, though we can tell in what respects they resemble living things and in what respects they differ from them. It may be helpful to think of viruses as a link between the living and the non-living. All right, I will pause again. I will be back. And we are back. I found a spot where that thing is caught in a trap. opposite of gravity, isn't it? Right. A brief account of the three laws of ideal gases. The first one is also called Boyle's Law because it was announced in 1660 by the English scientist Robert Boyle. It's funny, isn't it? 1600s, they were all at this stuff, and it wasn't needed, was it, for hundreds of years after? Don't forget all of this stuff. They didn't have calculators, didn't have anything, no power, nothing. It's very strange. But by Robert Boyle. According to this law, if the temperature remains the same throughout, the pressure upon a confined body of gas is inversely proportional to its volume. That means that if we reduce the volume by half, the pressure is doubled. If we reduce the volume to 1/10 the former volume, there will be 10 times as much pressure. The second ideal gas law is often called Charles' Law, after its discoverer, Jacques Alexandre César Charles, lived between 1746 and 1823, a French scientist. This law tells us that if the pressure of a gas remains unchanged, the volume is directly proportional to the absolute temperature. If the pressure remains at 15 pounds to the square inch throughout, the volume of a gas at 546 degrees will be exactly twice as great as that of a gas at 273 degrees. According to the third ideal gas law, if the volume of a gas remains unchanged, the pressure is directly proportional to the absolute temperature. Suppose that a given amount of gas confined in a container exercises a pressure of 15 pounds at 273 degrees. At 546 degrees, the pressure would be twice as great, that is 30 pounds. These, then, are the three laws of ideal gases. As we have seen, they would apply exactly only to a theoretical gases which are not found in nature. The gases that actually exist deviate from the laws to a greater or lesser extent. The Belgian chemist Van der Waals made a careful study of these deviations. He summed them up in a mathematical formula that is generally called Van der Waals equation. In this formula, he took into account two factors that are not considered in the ideal gas laws. 1. The attraction between molecules. 2. The fact that molecules occupy a part of the total space in a given container. The attraction, here we go, right? This is why I read it. The attraction between molecules is due in part to gravitation, the force that holds the planets in their orbits around the sun and that causes meteors to fall to the earth. But this force is far too weak in the case of molecules to account for all the actual deviations from ideal behavior. Some more powerful force must also be at work. Now, as you will read in another chapter, the molecules are made up of atoms, and the atoms in turn contain tiny electrically charged particles. When two molecules are close together, the electrical attraction between them is particularly strong. At the same time, the force of gravitation also operates. This combination of forces is known as the Van der Waals forces. They are most powerful when the molecules are closest to each other. All right, I shall move forward. Alrighty. Antiquity. The beginnings. Science is the sum of the thoughts and deeds of those who take the scientific point of view toward the universe in which we live. This point of view is always subtly changing, but in general it is based on the belief that within limits, the law and order of nature can be fathomed by the mind of man. For all its bewildering complexity, science points towards two main objectives. It seeks, in the first place, to learn about the world of living and non-living things. The chemist studies the building blocks of nature, molecules and atoms and ions, and the combinations they form. The physicist analyzes and measures the forces that he finds in nature. The astronomer directs his attention to the fathomless universe of stars and comets and planets. The geologist studies the structure of the earth, the meteorologist, the atmosphere, the biologist, the living things that people the earth. Living things that people the earth. The psychologist, the inner working of the mind. But science is not always content merely to learn about the world. Through its application to industry, technology, it is also concerned with modifying it as far as possible. The chemist transforms the materials that he finds in nature. From them he fashions explosives and medicines and fabrics and other new materials almost without number. The physicist seeks to harness the mighty forces of nature. Electric motors and hydraulic rams and aeroplanes bear witness to the success of his efforts. Through his profound knowledge of the Earth's structure, the geologist has made it possible to win vast mineral treasures locked up in layers of rock. With these treasures, man has reshaped his environment. The biologist has brought his knowledge of plant and animal pests to bear on the task of making vast areas safe for mankind. The meteorologist has taken the first steps in controlling the weather. Already he has made clouds release their accumulated stores of moisture in the form of rain and snow. So 1961, the meteorologist has taken the first steps in controlling the weather. Already he has made clouds release their accumulated stores of moisture in the form of rain and snow. Looking back from the 20th century, we discover many activities and events that we would today label scientific, and we can also identify thousands of men whose work justifies our calling them scientists. Newton. Yet we should remember that the word science, as we use it today, is a comparatively new word in the English language. It got its now accepted meaning only in the early part of the 19th century. What we call science was earlier labelled natural philosophy. Science today means a particular kind of knowledge. But back in the 14th century, when the English poet Chaucer used the word, he took it to mean all kinds of knowledge, arts and sciences alike. The word science comes from the Latin word meaning to know. Science, we have seen, represents one kind of effort to understand man's world and to modify it to suit his purposes. Newton. We shall never know exactly when this never-ending task began, for we have no written records of the first crude scientific gropings of man. We have only a few scattered relics which have been pieced together by the patient efforts of archaeologists. We do know that man's greatest scientific discovery, the use of fire, and his greatest invention, language, go far back in prehistoric time. It was in the prehistoric period too that man began to fashion the tools that first enabled him to survive and then to win mastery over other creatures of land and sea. It is only with the dawn of recorded history, some 6,000 years ago, that we come upon the first authentic records of what we now call science. We must seek them in the valleys of the Nile, the Tigris, and the Euphrates, for it is in these areas that we find the first traces of man's civilization. Okay, I will pause. I will be back. And we are back. Gave that a good little push. Okay, early Greek scientists. Travel broadens. The man who makes his way to foreign lands is likely to find his curiosity sharpened by new sights, sounds, smells, and tastes. He will be tempted to ask why things are so different in a strange land, and in his attempt to gratify his curiosity, he will acquire wisdom. So it was with the ancient Greeks. They were inveterate travellers, a seafaring and trading people. They built ships and sailed ships. They skipped from island to island and from island to mainland in the Mediterranean Sea. They founded colonies in many places around the Mediterranean. There were so many of these settlements, indeed, in southern Italy, that this region came to be known as Magna Graecia, Great Greece in Latin. The Greeks came in contact with older and more advanced civilizations. To the south were the ancient empire of Egypt and the highly civilized kingdom of Crete. To the east were vestiges of the old age civilizations of Babylonia and Assyria and the more recently established Persian Empire. In these centres of culture, the Greeks collected ideas as well as merchandise. They brought back these ideas to the homeland and to the many islands and coastal areas they had colonized. Greek science arose in the district called Ionia, a strip of land on the west coast of Asia Minor and a group of nearby islands. A number of cities had been established here by the Ionians and other Greek people. By the 6th century BC, Ionia had become a renowned centre of learning. The wise men of Ionia thirsted after knowledge. They sought reasonable explanations of all things. To them, what we call science was only a part of philosophy, the all-embracing search for wisdom. Philosophia means love of wisdom in Greek. The first of the great Ionic philosophers was Thales of Miletus. Like all early Greek thinkers, Thales was particularly eager to find answers to the questions: what is the world made of? What is the relation of the world to the rest of the universe? He believed that the world's stuff, of which all things were made, was water. It was colourless, shapeless, always changing and always moving, yet it flowed according to a pattern or cycle that did not itself change. Water fell from the sky as rain. It passed into rivers, lakes and seas and through bodies of plants and animals. Then it returned to the sky to fall again. The cycle was constantly repeated. Its pattern was forever fixed. Thales and his Ionian colleagues noted that the patterns of many natural events were so regular that they could in some cases be predicted. They came to the conclusion that all nature follows a pattern, that it obeys certain definite laws, and that it does not act through the whim of capricious gods. This idea of natural laws was not accepted by all of Thales' contemporaries, nor it is universally accepted today. This idea of natural laws was not accepted by all of Thales' contemporaries, nor it is universally accepted today. Iona's neighbours, the Lydians and the Medes, cried "Miracle!" when the sun was obscured while they were engaged in a fierce battle. Thales had predicted many months before that the sun would be darkened on that particular day in the spring of 585 BC. According to the Greek historian Herodotus, the combatants were so impressed or terrified that they promptly made peace. Of course, Thales himself realized that there was nothing miraculous about an eclipse of the sun. Now this is 600 BC, right? He knew that it takes place when the moon passes between the sun and the earth. He had learned much about eclipses in Egypt and in Mesopotamia, where he had travelled on business. This wise philosopher was a successful businessman dealing in salt and oil. In Mesopotamia, Thales had met and talked with the temple stargazers. Their records, kept over many years, showed that an eclipse of the sun usually took place at intervals of 18 years and 11 days, or after each 223 risings of the moon. With this background of information, it was easy enough for Thales to predict the date of the next eclipse of the sun in his part of the world. In Mark Twain's Connecticut Yankee in King Arthur's court, the hero saves his life by making a similar prediction. Now, there it is again. So, 18 years, 11 days, and a certain amount of hours. That is a series, and there were how many? 223 risings of the moon. So you get an eclipse, of the sun, solar eclipse, and after another 223 risings of the moon, it will happen again in that place. And what happens, if we had no record, we all woke up tomorrow, never been here before, and like, oh, this is cool. And apart from the tax, and apart from those people, why are they telling us what to do? That kind of thing. Nobody had any idea. You're going about your business, used to the sun coming up, and one day, the moon blocks the sun. You'd be like, what is going on? That will not happen again for 18 years, 11 days, was it? And a certain amount of hours. When it happened the second time, who would have remembered the time before that? 18 years previous. Oh, I remember. Something like this happened 18 years ago. 18 years and 11 days ago. Oh, okay. Yeah, all right. Well remembered. So who would have written that? So somebody had to write this down and write the second one down. That's 36 years, right? Twice is not a pattern. It's a coincidence. So then it would have happened again. Another 18 years, 11 days, so that's what, 54. 54 years for it to happen 3 times. Now, it wouldn't have only happened here, it would happen in loads of different places all over the planet Earth. But what I'm saying is, 3 times, that's 54 years. For it to happen again, that's 72 years. So somebody to have seen 4 parts of the same series of the eclipse, that's 72 years, right? If nobody, the first people to start taking note, to then learn, when all of the eclipses do happen, that would have taken so long, right? You might have a cloudy day, like really bad weather, and miss a whole 18 years. So you wouldn't know until 54th year. That would have been your second. Look, it's the amount of knowledge, right, like this, that has to be catalogued, recorded, just for 2. It's 18 years. First one, 18 years. Like, and to think, I think this is a series now. Somebody would have died, passed it on. When did he say? No, what calendars did they? Look, it's a hell of a feat, right? It really is. It makes you wonder. It makes you wonder. What would be the alternative to that if that was a lie? Somebody would already know what the sequence of solar eclipses and lunar eclipses are, but they have made this story up to distract from the truth. If somebody did already know when and how, look, it's just one of those things, right? Now, where are we? Eclipse of Earth. Was enough. During his travels in Egypt, Thales observed the practical methods of land measurement, or as the Greeks called it, geometry, used by Egyptian tax assessors. It occurred to him that this complicated system of triangles and rectangles and spheres could serve some other purpose in measuring fields or calculating the size of pyramid blocks. He came to realize that certain definite principles apply to all triangles, angles, rectangles, and so on. Thus, he discovered some of the fundamental propositions, you may call them truths or facts, of plane geometry. He discovered, for example, that if 2 sides of a triangle are equal, the angles opposite these sides are also equal. This proposition proved to be difficult for beginners to understand. It became known, therefore, as the Pons Asinorum, or Arce's Bridge, because it is also difficult to get a donkey to cross a bridge. Thales showed that when two straight lines intersect, the vertical opposite angles are equal, that a diameter cuts a circle into two equal parts, that the sum of the angles of a triangle equals two right angles. He proved that the sides of similar triangles, triangles whose corresponding angles are equal, are proportional. The last discovery made it possible for Thales to perform several practical feats of measurement which amazed and delighted his contemporaries. Plutarch tells us, for example, that King Amasis II of Egypt admired Thales particularly because merely by placing his staff at the end of a shadow cast by a pyramid showing two triangles formed by contact with the sun's rays, the Greek philosopher was able to measure the height of the pyramid. In his own day, indeed, Thales' reputation was based not so much on his philosophical theories and his geometrical pioneering as on his skill in measuring pyramids and predicting an eclipse. Thales had a pupil, Anaximander, 611 to 547 BC, who was also interested in the nature of the basic world stuff. He came to the conclusion that it was an indefinite substance, infinite in quantity. From it, he taught the heavens and the earth were formed, and to it they would of necessity return when their day was done. Anaximander held that the universe was a cylinder, fitting inside other larger cylinders like a child's set of nesting blocks. What on earth would make somebody in 600 BC think the universe was cylinders? He prepared a map of the world, obtaining his data from the sailors who frequented the city of Miletus, where he lived. Somewhat later, another citizen of Miletus, Hecataeus, born in 540 BC, made a more detailed and accurate world map. On one of his voyages, he sailed along the coasts of the Black Sea. On another, he made his way to the Strait of Gibraltar. Here he saw the famed Pillars of Hercules, the promontories at either end of the strait. Now, 600 BC now. Now we're talking 600 BC, and there were people going up and down the Mediterranean to the Straits of Gibraltar, sailing the Black Sea. What? See, there's all of these things, all of this stuff, right? When we look at it all together, there's lots of little speed bumps. I'm going to just mention a speed bump coming up very, very soon, which is why I'm actually reading this. Like a child's set of nesting blocks at either end of the strait. Another man of Miletus, Anaximenes, flourished 6th century, taught that air, not water, was the first principle of all things. He linked this air, or pneuma, with the very breath of life. Anaximenes believed that the earth was in the form of a flat, round disc, floating in a sea of air, and that the heavenly bodies revolved around it. Heraclitus of Ephesus, 6th century to 5th century BC, held that fire was the first principle of all things. Fire was transformed into other elements, and these other elements in turn into fire. All things, he taught, are forever in a state of flux. There is no birth and no death, but only a ceaseless transformation of the restless elements. Heraclitus was a solitary and forbidding figure. Because his doctrine seemed to men to be cheerless, he was known as the weeping philosopher. Democritus of Miletus, some say, of Abdera, who lived in the 5th century BC, was famed for his atomic theory of matter. He developed the idea, first advanced by his master Leucippus, that the world is made up of infinitely small particles of hard solid matter that cannot be cut up into anything smaller. The Greek word for such an indivisible piece of world stuff was atomos. That which cannot be cut, from it is derived our word atom. According to Democritus, atoms differed from one another in shape and size. Atoms of water, he said, were smooth and round and glided over each other. Atoms of iron, on the other hand, were prickly and rough and clung to each other like cockleburs. The atoms had to exist somewhere. So Democritus conceived of an infinite void through which the atoms ceaselessly moved. When they came together, they formed all things upon the earth and in the heavens. This happened purely through a chance which caused them to swerve a little in their paths. See, now this is where the atoms and it's introduced. What are the chances? Much of what we know about Democritus' teachings come to us through a great philosophical poem on the nature of things, written long after Democritus' death by the Roman poet Lucretius, a contemporary of Cicero and Julius Caesar. We discuss this poem in a later chapter. Don't worry, I will not be stopping there. Today we also believe in the existence of atoms, but our atoms have little in common with those of Democritus. For one thing, the atom, according to our present ideas, is not the smallest existing particle, nor is it indivisible, for atoms can be broken up. Our notion of how atoms combine differs from that of Democritus. Okay, we now come back to the world stuff theory. The one that was most widely accepted by the ancients was the doctrine of the four elements. It was set forth in a poem of nature. Don't poem me. Empedocles was a poet and a philosopher. He was also a prophet and a mystic, and many of his contemporaries were convinced that he was more than human. Empedocles taught that there were four elements: water, air, fire, and earth. There were also four quantities: cold, wet, hot, and dry. Well done. Any two of the qualities made up one of the elements. Thus, water was wet and cold, air was wet and hot, fire was hot and dry, earth was dry and cold. The elements were constantly being brought together by love, and just as constantly parted by hate. For Empedocles held that these two forces shared the rule of the world. Human flesh and blood, according to Empedocles, were made up of equal quantities of the four elements. Bones consisted of 1/2 fire, 1/4 earth, and 1/4 water. Ordinary water was composed mainly of the element water, that is, wet and cold, but it had a little of the other elements in it. Absolutely pure water was an essence that was quite beyond the comprehension of human beings. The idea that the universe can be broken down into more or less stable elements was a forerunner of modern theory. But of course, we believe today that the elements are neither so few nor so simple as Empedocles had imagined. His theory was widely accepted for 2,000 years or so, when Mark Antony pays tribute to dead Brutus in Shakespeare's Julius Caesar. His life was gentle, and the elements so mixed in him that nature might stand up and say to all the world, "This was a man." Right, here we go. The Pythagorean Brotherhood. Among the most important factors that influenced the development of science in Greece in the early days was the curious group known as the Pythagorean Brotherhood. It was at once a religious cult, a philosophical school, and a political movement. The founder of the group, Pythagoras, was born at Samos, an island in the Aegean Sea, in the early part of the 6th century BC. The details of his life are shrouded in mystery. According to his followers, he travelled widely. In Phoenicia and Syria, he sought to learn religious rites and doctrines. He spent many years in Egypt and became acquainted with the whole range of Egyptian learning. He was in that ancient country, so the story goes, when it was conquered by King Cambyses of Persia. Pythagoras was carried prisoner to Babylon, where he conversed with the sages of the Persians and the Chaldeans. Upon his release, he settled in, I thought it said Croydon, but it's not, it's Croton, a Greek colony in southern Italy. Here he set up a philosophical school attracting great numbers of the noble and the wealthy. He enrolled 300 of this elite in a select fraternity whose members were bound by a vow to Pythagoras and to each other to follow the religious rites prescribed by the master and to study his system of philosophy. As time went on, the school dabbled in drugs, joking. As time went on, the school dabbled in politics and it won great influence among the Greek colonies of southern Italy. Now, here we go, right? A wealthy citizen, Cylon, who had been refused admission to the Pythagorean Brotherhood, succeeded in stirring up the people against Pythagoras, and the philosopher was banished. The date and details of his death are unknown. The Pythagorean Brotherhood continued to be powerful until about 450 BC. The Pythagoreans, says Aristotle in the Metaphysics, devoted themselves to mathematics. They believed that its principles were the basis of all things. They thought of numbers as expressing not merely the relationship between existing things, but as their very essence, a kind of basic world stuff. This extreme viewpoint led the Pythagoreans into many absurdities. They identified the number 1 with reason because it was unchangeable. The number 4 they taught was justice because it was the first square number and the product of 2 equals. 2 times 2 equals 4. They associated the 5-pointed star, the pentagram, with health and well-being, and they used this symbol as a secret recognition sign among members of the Brotherhood. In later times, the pentagram was debased to a magic charm, which was supposed to ward off evil. So see here how they throw in the suggestion of the pentagram and that it was used as a secret, symbol amongst the Brotherhood. Steeped in geometry, the Pythagoreans sought to express numerical relations by means of geometrical figures. Thus they referred to certain numbers as triangular and to others as square. According to this system, the series 1 plus 2, 1 plus 2 plus 3, and so on is made up of triangular numbers because it can be represented thus. For all their dabbling in genius fancies, the Pythagoreans made many solid contributions to learning, particularly to mathematical knowledge. Pay attention here. One of their best known demonstrations concerned right triangles. In a right triangle, the longest side, the one opposite the right angle, is called the hypotenuse. The Pythagoreans showed that the square of the hypotenuse of a right triangle is equal to the sum of the squares of the other 2 sides. The Egyptians knew that this equation held true when the ratio between the sides was 3 to 4 to 5. Pythagoras is said to have been the first to show that the equation works in all cases. It is still called the Pythagorean theorem. The Pythagoreans worked out many of the theorems still to be found in geometry textbooks, particularly those involving parallels, triangles, quadrilaterals, and polygons. They identified many of the properties of prime numbers, those divisible only by themselves and by 1. They also worked out a system of irrational quantities, those which, like the square root of 2, cannot be expressed by ordinary numbers. They made notable contributions to musical theory. Tradition has it that Pythagoras, visiting a blacksmith shop, was struck by the different musical tones produced by hammers of different sizes pounding on metal. He tried to fathom the secret of this impromptu anvil chorus and discovered that musical intervals depend upon certain numerical ratios. Now, what I am going to say here, right? How long have I been going? 44. I'm going to stop it at 45. Folks, this is all with no electricity, no calculators, no anything. This claims that they worked out the whole numbers. Where was it? By 4-sided figures and polygons. They identified many of the properties of prime numbers, those divisible only by themselves and by 1. No calculators, nothing to fall back on. no reference guides, but they did all of this stuff with no electricity, meaning no electronic devices, no calculators, no nothing. All of this stuff. This is what people are not understanding. They had nothing. BC. But all of this was all discovered, and it all piggybacked each other to the 1960s. And here is the story that everybody needed to be in place by the end of the decade, 1969. Look, we've already passed the 45-minute mark, so I might as well go close to the hour. But all of this stuff, this isn't a history lesson. This is a story. The names, see how these names keep popping in? Where did this information come from? Where did the people who wrote this stuff, where did they get all of this information? They didn't. It's been made up. The majority of this has been made up. Right, I'm going to pause again and probably do one more blast. All right, one last push, head for the hour. Right, so this is straight after what we were just talking about. Philolaus, 5th century BC, a follower of Pythagoras, worked out an ingenious theory of the universe, corresponding to the Pythagoreans' perfect number 10. There are 10 celestial bodies in the heavens, according to Philolaus. The Earth, the 5 planets known in his day, the Sun, the Moon, the counter-Earth, the Pythagorean invention, and the hollow sphere containing the fixed stars. All these bodies are spheres. The universe itself is spherical in shape and limited in area. At the center of the universe is a central fire around which the heavenly bodies, including the sun, revolve. We cannot see the central fire because the hemisphere in which we, meaning the Greeks of Philolaus' day, live is always turned away from it. We cannot see the counter-Earth for the same reason. As the spheres revolve around the Earth, they produce wondrous harmonies. The tone produced by each sphere depends upon its distance from the central fire. If we cannot hear this music of the spheres, it is because our core senses are not sufficiently attuned to it. It is easy to ridicule this account of the workings of the universe, yet, like many notions of the Pythagoreans, this fanciful speculation contained a grain of truth. For, as Copernicus himself pointed out, the doctrine of the central fire foreshadowed the Copernican theory that the Earth and planets revolve around the sun. Right, the golden age of Greek philosophy. Now, I've already underlined a couple of things here. Here we go. Here we go. Aristotle, another legend, right? Oh, that container's going off. So it's all on rappel, remember? Spinning. Right, well, so you thought Galileo was good, okay? You thought Newton was good. Aristotle! Here we go. Aristotle wrote on poetry, drama, politics, ethics, rhetoric, metaphysics, psychology, astronomy, meteorology, physics, mathematics, anatomy, and biology. As a scientific writer, he introduced 2 important innovations. He used diagrams to illustrate difficult points. He reviewed and criticized all previous writings upon a topic before giving an account of his own observation and ideas. Sounds a little bit like me. Much of our knowledge of the scientific accomplishments of the early Greeks comes from Aristotle's reviews. His scientific doctrines in part reflected the thinking of the times. In part they resulted from his own keen powers of observation and analysis. Today we reject a good many of his findings, yet we must remember that the data at his disposal was generally pitifully inadequate. Aristotle thought of the heavens as a series of crystalline spheres set one within the other and turning about the earth, which was at the centre. Next to the earth was the sphere of the atmosphere. Then came 4 spheres corresponding to the 4 elements: earth, water, air and fire. Beyond the sphere of fire was a region containing ether, a mysterious substance which was to be found in all heavenly bodies. Then came the 7 planetary spheres, each carrying a single planet, and another sphere carrying the fixed stars. At the outermost limits of the universe was the sphere of the prime mover, the first cause, which was the source and origin of all motion and life. The elements, earth, water, air and fire, contained in 4 of the outer spheres, were also to be found upon the earth. They were the building blocks of all things, living and non-living. Aristotle divided the physical world into 2 realms, the organic and the inorganic. He held that the organic is marked by the possession of life, or soul. He arranged or classified living things according to the amount of soul stuff they possessed. His ladder of nature, as it was afterwards called, began with the lower plants and worked up through sponges, jellyfish. They always get a bad rap, jellyfish, don't they? Insects, reptiles, and fish to whales, mammals, and man. He believed that everything in the world was created for a purpose, that the end to which a thing is to be put determines its shape and structure. In his biological work, based on first-hand observation, Aristotle is at his best and comes closest to modern scientific method. For example, he discussed competently the life and breeding habits of about 540 species of animals. He accurately described the 4-chambered stomachs of ruminating animals such as cows. He made a number of acute observations on the development of various forms of marine life, including the octopus and a species of dogfish that carries its young somewhat like a mammal. In some cases, Aristotle's findings have been verified only in comparatively recent times. It's ridiculous. For almost 2,000 years after his death, Aristotle reigned as the supreme authority in scientific matters. He was held to be the master of those who know, as Dante put it. Many of his ideas, particularly those that had a Pythagorean basis, were adopted by the church. In the Middle Ages, when interest in scientific experiment and direct observation was at a low ebb, Aristotle's word was law. He himself said it. Ipse dixit was the argument that medieval schoolmen used to prove the truth of many a scientific observation. Under these circumstances, the errors of Aristotle, particularly in physics and astronomy, held up scientific progress for centuries. Listen to this. Nothing happened for centuries. Aristotle held, for example, that the essence of air is levity, lightness, rather than gravity. Weight. Therefore, a large amount of air should weigh less than a small amount. He also taught that the forces that move things on Earth are different from those that move the heavens. It was not until the 17th century that Galileo and Newton caused these beliefs to be discarded once and for all. Galileo showed that 2 bottles containing air weigh more than 1 such bottle. Newton demonstrated that the forces that move comets and planets through the skies are the same as those that move stones and apples on the earth. How did he show that? How did he show that? Newton demonstrated that the forces that move comets and planets through the skies are the same as those that move stones and apples on the earth. How did he demonstrate that? How could somebody demonstrate that even today, right? This is the thing. Ironically enough, Aristotle would have been the first to protest against the slavish obedience in the Middle Ages to his scientific and philosophical views. He himself maintained that all our theories concerning the world around us are but provisional, and that they should be abandoned if they are proven to be erroneous. It was not his fault that lesser men, dazzled by his greatness, blindly accepted his teaching as gospel, and thus held up for a long time The March of Progress. Right. I'm going to call it there. Before I do, I'm just going to press play, because I love this bit.
Just always be cautious of the Dunning-Kruger effect. You put in a little bit of work and you have an idea, and then you think your idea is right, and that Einstein is wrong, and Newton is wrong, and that everybody's wrong, and that all of modern astrophysicists are wrong. That's bold.
Bold. Just explain. How, where is the logic behind the sun being directly behind the moon during a solar eclipse? Where is the logic? Where is the logical explanation for why sun is directly behind the moon during a solar eclipse? There is no light delay. There are no photons. There is no 8 minutes and 20 seconds delay anywhere, because when the moon is in front of the sun, we see the shadow. We are in the sweet spot shadow. It is the sun that is being blocked by the moon, not photons that have traveled for 8 minutes and 20 seconds, because if that were the case, the sun would have shifted. So Dunning-Kruger, just one logical explanation from one of them. They're wrong. All of the physicists, the scientists, it's not about Dunning-Kruger, it's about common sense and logic. That's what it's about. Hour 56:44. Let me pause. I might be able to squeeze another couple of minutes of something in. I'll be right back. The face of the sky. I don't know if I'm going to read this page in 3 minutes. The planet on which we live is never still. Like some sparkling jewel, reflecting the dazzling light of the sun, it moves ceaselessly through the blackness of outer space. Spinning on its axis, it rushes around the sun at the rate of 18 miles per second. At the same time, it speeds with the rest of the solar family toward a distant bright star Vega.